Bismillahirrahmanirrahim. Greetings. The concept of function relation and their inverses is in the curriculum of mathematics from grade school all the way to high school, college, and way, way beyond. Now, in this video lecture, and maybe 2 or 3 more to follow, I'm going to discuss about the subject of inverse function. Now, I'm assuming that the student or the audience are already familiar with the definition of function. And I have already uploaded 2 or 3 video lectures about this concept, the concept of function relation, and I strongly encourage you to possibly watch those video lectures. You can find them in my channel, and also in the comment section I'm going to give the site link of those videos for your reference. Okay, then let's get started, shall we? Now, I have written most of the stuff for those that they like to take notes. And sorry, I don't have advanced equipment. No, and for those that they like to take notes, I'm repeating myself. I have put them in writing, and I'm going to a little bit zoom it so that it's more visible. And I don't think you will be having problem writing. I try to write them large enough so that it's readable. Now, addition, subtraction, multiplication, and division, the arithmetic operation that we are usually exposed in the first grade elementary school, they are functions. They are functions. They have input and they have unique output. And that's exactly what characteristic of function is. So the input of this operation, arithmetic operations, are in the set of numbers, or 2 numbers at a time. And the output is also another number, but is unique. In the language of calculus, we call it single-valued function. Single-valued function. But in college algebra and pre-calculus, usually the output, which is unique, we call it as a function. Now, they are called binary operation, as the name is concerned, because you give 2 numbers at a time for getting a unique number out from the operation, whatever it is, addition and subtraction. Now, addition and subtraction are same thing. I repeat myself, addition and subtraction are, on one hand, they are same thing, on the other hand, they are inverse of one another. Sounds like it's contradictory, huh? It's contradiction. But it's a fact. And we will be seeing and believing. You will be persuaded that is the way it is. So I repeat myself one more time. Addition and subtraction, same is true with, of course, multiplication and division. They are equivalent. They are paraphrase of one another. In one sense, they are inverse of one another in another sense. Now let's see what that means to make it a little bit more clear. Now I have some examples I put. You are welcome to take a note of this if you wish so. Now let me give you a next one. Now, 3 plus 2 is equal to 5, and 5 minus 3 equals to 2 are 2 arithmetic expression. Now, with respect to equality, these 2 expressions are equivalent. They are paraphrase of one another. And the equality itself is a relation that has the property of reflexive commutativity and also the transitivity. So it's, you know, in abstract algebra they call it that they partition the set into equivalent classes. But that is a little bit aside. But equality itself is a relation. Now, with respect to the equality, I'm repeating myself, this arithmetic expression and this arithmetic expression are equivalent. They are paraphrase of one another. They are synonym. Now, with respect to the operation, this one is addition and this one is subtraction. They are inverse of one another. Do you follow me? So in one sense, they are equivalent. They are synonym. They are paraphrase of one another. In another sense, they are inverse of one another. Now let's see what that means with some other examples. Now I have written again if you like to take a note. Now I have another example that is a change making machine that we are very used to it, and every day we are kind of exposed to that. Let's see how that can make this concept a little bit more explicit so that you don't think there are a contradiction of what I said. Now, suppose that I have $5 in my pocket and I'm in Manhattan in New York, and I want to do some shopping, and I don't want whatever I buy from grocery exceeds $3. I need $2 to pay for the subway to go back home. Okay? So I go to grocery and I pick few things, let's say 3 things. One of them, the price is $1.75. The other one is 0.75 cents, which is $0.75. And the other one is 50 cents, which is half a dollar. Now I add them, they end up to be 3. Then I take my cell phone out and I subtract that 3 out of 5, and I'm left with 2. So I'm very happy that I'm left with $2 to go back home, and I have bought few snack or something so that I can eat in the train before I reach the home. You follow me so far? So when I go to the cashier, I notice the cashier does it differently. So I give him the $5 to the cashier puts it aside next to the machine, and then adds it with the machine. Exactly the way I add it. 1.75 plus 0.75 plus 0.5, he ends up to 3. Then he opens the drawer of that machine and he takes $1 out and he says 4. And he takes another dollar, he says 5. Then two single dollar has taken out of machine. He gives it to me. Then he puts that $5 that he got from me inside the drawer, and he closes that one. I'm sure you have seen that 10 times a day. Whenever you go to shopping, that's what you notice it. No. In that case, look what happens. The cashier add 3 and 2, and he end up with the 5, exchange this with the 5, and what I did, I subtract 3, the grocery stuff that I bought from 5, and I end up with 2. Now look at this. These 2 arithmetic operations, arithmetic expressions are equivalent. You can see it for yourself. They are doing same thing, but in different way. So they are paraphrase of one another. Now, with respect to the equality, they are paraphrase. With respect to addition and subtraction, they are what? They are inverse of each other. So on one hand, they are what? They are equivalent. On the other hand, they are what? They are inverse of one another. Very interesting, isn't it not? Now, what I will do now, because algebra generalizes arithmetic. So let's go to algebra and see how we can relate this one to the algebraic expression, and see how we can generalize the idea for that. Okay, so that will be the next one. Again, you are welcome to take a note, and of course you have the upper hand of pausing and zooming so that you can see it better for yourself. So the next one is concept of inverse function, analytical and geometrical. So we want to study about concept of inverse function analytically and geometrically. Now, I made the example, simple example, y equals to 3x, and then I solved this one with respect to the equality. With respect to the equality, I solved them and I wrote x equals to y over 3. Now, these two expressions with respect to the equality are what? Are in a sense equivalent, in another sense they are inverse of one another. Let's see what that means, being equivalent and being inverse of one another. Now, by the way, I wrote something here that I'm glad I noticed it, that is important to mention so that you read it accordingly. Now, ROC is abbreviation for rule of correspondence. Here I say y equals to f of x equal to 3x. That is correct. I didn't make mistake. And if you read it that way, it's not wrong also, but I do not recommend you to read it that way. So how do you read this expression is that you say y is, this equality, don't read it equal, say is. So y is a function of x, and then this equality, you read it with rule of correspondence, with the rule of correspondence of 3x. So again, how do you read this one? You say y is a function of x with the rule of correspondence 3x. Rule of correspondence is in reality what the function is. The rule that tells you how x and y correspond to one another. Now here, for every x that we assume number for, 3 times that will be the value of y. So that is the rule that x and y are corresponding to one another. So the name again is rule of correspondence. It's very important to read it that way so that you really understand the concept very good and you're not kind of parrot-like memorizing. Now, I have written again, please take a note of it, and it's very important the way that I read it, you read it the same way. Okay, now let's go to now I'm going to discuss about analytical graph of these two expressions that I put for you, and compare it that way. Let me see. Now here, the rule of correspondence, y is a function of x with rule of correspondence to be 3x, is same as y equals to 3x. Is that right? Now in the graph of that, the analytical graph is that when x is 0, y is 0. Is that right? Y is 0. X is 0, y is 0. So when x is 1, when we assume value 1 for x, then y will be 3. Is that right? And when we assume, x assume the value of 2, y will be 6. Is that right? 6. So this is what, with respect to this rule of correspondence, this will be what, of course, I should have given some dot here, which means can go for forever. And I selected this so that easy numbers to just remember and better comprehend it. Now, look what happens when I do it that way, that we say x is a function of y. All right? The previous one I said that they were what? They were equivalent. Y equal to 3x is equivalent to x equals to y over 3. So if I write it like that, look what happens. X is a function of y with the rule of correspondence that y equals to 3 over x. Now, when y is 0, x is 0. Is that right? When y is 3, x is what? X is 1. When y is 6, x is what? X is 2. When y is 9, x is 3, and so on and so forth. You can go for yourself. Now look at this one. These two analytical graphs are same. These two analytical graphs are same. Now, this one, y is a function of x with the rule of correspondence 3x, is using the operation of multiplication. And this one, x is a function of y with respect to the rule of correspondence, y is y over 3, but with respect to that rule is what? Is giving exactly same. Look at that, it gives me exactly same, what? Exactly same graph. But this is using multiplication and this is using division. So in sense of multiplication and division, these two are inverse of one another. With respect to the equality, the meaning of equality, these two are both are same graphs, analytically. I haven't gone to the geometrical interpretation of that yet. So again, you can keep a note of it if you wish, and again notice that these two, the two different operations, but they give same analytical sets. The graph, the analytical graph of them are same. Now let's look at the graph of them, in that you are familiar with that, with sketching the graph. Now, we know that two distinct points determines a unique line. Now, what I just said is not true if we change the geometry. And if I do not say two distinct points, again, you can give me a counterexample to show that is not correct. Because mathematics is such a meticulous subject, so you should be very precise in the word that you use for that. So in the plane geometry, another name for plane geometry is Euclidean geometry. In Euclidean geometry, two distinct points determines a unique line. If you don't say two, you say two. If you don't say, the word distinct, the 2 points can be on the top of each other, superimposed on the top of one another, so becomes 1 point, and with 1 point, infinitely many lines can pass. So it's very important to emphasize that you're working in Euclidean geometry, not other geometries, because in other geometry that is not true. Between 2 points, maybe infinitely many lines can pass, and maybe no line can pass, but that is belong to other geometries. Now, the reason I brought that one up, because we need two distinct points to sketch the graph. And I don't say at least we need two, in another word. Two distinct points is necessary and also sufficient to sketch the graph of any linear function, because of this characteristic of two distinct points determining a unique line. Now let me go through this one for you. And well, maybe I should cover this part so that I can come to that. Now here, y is a function of x, is that right? Y is a function of x. Here, 2 points I select. One of them, let's say the trivial point 0, 0. Another one, let's say 3 points in this way. When I give to x1, when I assume number 1 for x, y will be 3. You see that? I put arrow, you can see that. So 1 arrow goes to 3. Is that right? Now, when I give 2 to the function, then what happens? 2, I give, the arrow goes up, you see that? And this is the point. Let me designate the point. This is the point, and this is the point. 2 distinct points determines a unique line. So my line will be drawn. And that is the graph of what? Of 3x. Are you with me? Now let's see how we sketch the graph of the other one. Just this one. Now here x is a function of y. The rule of correspondence between x and y is still the same, remains same. We have not changed the rule of correspondence between x and y because we noticed that the analytical graph of them, they were same. Now look what happens for this one. When I assume value of 3 for y, look what happens. The arrow goes this way. So x will be 1. So 1 is paired with 3, and when y is 6, you see that? X will be what? X will be 2. So look at that. The analytical graph of them, they were same, and the geometrical graph of them is also same. Because the rule of correspondence between x and y was not changed. All right? But the operation, one of them is multiplication, and one of them is what? Is division. Now comes the point that we do change the rule of correspondence, not change, but we interchange the rule of correspondence between x and y, and see what we can come up in that case. So next one we are going to what? We are going to interchange the rule of correspondence between x and y. Now here, we go back to the same point. Y is a function of x with the rule of correspondence 3 times x, all right? Now, I interchange the rule of correspondence between x and y. Now I say x is a function of y with the rule of correspondence 3y. You follow me? So the rule of correspondence between x and y has changed. Now let's see what happens to the analytical graph of that, and what happens to the what? To the geometrical graph of that, and see what we will notice. Does analytical graph of that gives us any hint? Does it give us any clue how the graph of the geometrical graph of that should be looking at? So we are kind of, the analytical graph is going to assist us to give us the impression, the idea, how the graph, the geometrical graph should be looking at, and how we can achieve that one. Okay, now analytical graph of that will be, I left it a little bit blank so that you can see that for y is a function of x with the rule of correspondence, y equal to 3x. When x is 0, y is 0, is that right? When x is 1, y is 3, is that right? And when x is 2, y is 6, is that right? When x is 3, y is 9, and so on. So I did put some dots here, going forever. And I select some number. You can also select negative points, negative numbers. Doesn't make any difference. Now I have interchanged the rule of correspondence between x and y. Here x is a function of y with the rule of correspondence that x is 3y. Before y was 3x, now x is 3y. The rule of correspondence between x and y has been interchanged. Now, let's see how the analytical graph of that will look like. Now here, when y is 0, x is 0, is that right? Trivial. When y is 1, x is 3, is that right? When y is 2, x is 6. When y is 3, x is 9, and so on and so forth. Now, looking at the analytical graph of y equals to 3x, and analytical graph of x equals to 3y, we notice that x and y, the order pair, they have been switched. You see that? 1, 3 become 3, 1. 2, 6 has become 6, 2. Do you notice that? And we want to see what kind of clue that gives us as far as the geometry is concerned. Looks like it gives us the idea that the vertical axis or y-axis and horizontal axis, x-axis, are going to be interchanged. And see how we can do that and how we can come up with interpretation of this one, looking at that to see how the graph of that, geometrical graph of that will look like. Now, let me see if I have, well, I have another one again for you, is a little bit more data giving you in a sense. So it doesn't hurt for those of you who like to take the notes. And also, I will be repeating what I just said. So it's not bad to discuss this one also. So again, y is a function of x, and that is when x is 1, when x is 1, y is 3. When x is 2, y is 6. When x is 3, y is 9, and so on and so forth. Now, I interchange the what, the rule of correspondence, I interchange x and y. The rule of correspondence between x and y has been interchanged, all right? I didn't solve it for y. I interchanged the rule of correspondence between x and y. And look what happens. When y is 1, x is 3. Look at these two. When y is 2, x is 6. Look at these two pairs. When y is 3, x is 9. So very clearly you notice that the x and y, the order pair has been what? Has been switched for each of them. Now I have generalized this one in the x1, y1, and you can see x1, y1 becomes y1, x1. x2, y2 becomes y2, x2. x1, 3, y3 becomes y3, x3, and so on and so forth. So what kind of clue is it giving to us? How does the graph of these two will look like, and how can we get the graph of this one from this, or the graph of this one from this? By graph I mean geometrical graph. Because here, if I know this one, I can very easily write this one. Just interchange, switch x and y, you get the graph of this one, the analytical graph. Now, we want to know how we can do that geometrically, all right? Now, let me see, I have this one here. Well, I have it, but I had something else to do it. But let me just go over that, but there is more to come for that. Now, the graph of y equals to 3x, the geometrical graph. The geometrical graph of y equals to 3x is I give values for x, 2 distinct points is sufficient to sketch the graph of a linear. We have gone over that. This will be the graph of that. Now, for this one, the values are selected from vertical axis, from the y, because they are both number line. So here, look what happens. When y is 0, x is 0. Okay, this is 1 point. When y is 1, you see that? When y is 1, x is 3. So one of the points, y is 1, x is 3 is this point, and 2 points is sufficient to sketch the graph, but I give another point. When y is 2, x is 6. Is that right? You see that? So I have 3 points in fact. And the line, the graph of that is sketched. Now there is more into that. But for further discussion of that, how they work and how the analytical graph can help us to come up with a geometrical interpretation, geometrical graph of that is very interesting. So that is going to be left for the next video lecture. Okay, then I thank you very much for watching. As always, I wish you prosperity and happy time. And we will be seeing each other soon for the 1 or 2 more lectures. Okay, then until then, so long.